example 6, everything that we had up here, past knowledge, found those vertical asymptotes for us. And in fact, and it was so long ago we've maybe forgotten, but we did do the division way back when with our hyperbolas to figure out how our graph was going to behave as it approaches 0. And so that y equals 2 is actually a horizontal line down here. Oh, that's in the way. There we go. And notice it's not an asymptote for the whole graph. In this case, it kind of feels like it is, but it might not be for the whole graph. But what's happening is our graph is approaching that 2, that y equals 2, as we get to 0. And then what we were adding today was the limits of the asymptotes of the partial fraction decomposition, and saying the limit of f of x as x approaches -2 from the left. This would be going down, so that would be -infinity, and that matches the left portion of the entire graph. And then the limit as x approaches 2 from the right for our graph, this portion has the same end behavior as our final product right there. So just continuing to add pieces to what we know about hyperbolas, with the understanding that there's a lot more out there, lots more math that can be done with hyperbolas at college. And that's why you'll often see so many math courses that are offered at college. Speaking of college, I can segue. I was registering my daughter for college. They explained to us how to transfer credits. And I thought, here's a perfect thing for us to talk about. Oh, let me do it. When we get done this year, and when your grades are posted at Pine Tech, you need to call them and ask them for an official transcript. Let me switch that. There it goes. And that official transcript is what you take to the registrar's office, wherever you end up going to school. And that's where they transfer those credits over, so you don't have to retake math courses. But it has to be an official transcript, and they said make sure your students don't forget about it, because they've had students that were getting ready for graduation, and they sent them a letter that said you can't graduate because you're short math credits or AP Stats credits or whatever. And the student shows up and says, but I did those. I did them in high school. And they say, we never got the official transcript. And then there's all kinds of scrambling that happens when they're supposed to be graduating from college. So, pardon me. I said make sure your students know, get the transcript the summer after you take the course, hang on to it, make sure you turn it in. So seniors, put that on your to-do list. Everybody else, a little tougher, you might want to start a file so that when you're done, you've got one file with all of your AP and or college and schools credits. So today, systems of inequalities in 2 variables. Lots of review, but I think there might be some pieces in here that we may have forgotten a little bit. Not this first one. Graphing a linear inequality, I don't think anybody's going to have trouble with that. Graphing lines, but graphing them when it's greater than, less than or equal to, greater than or equal to. Graphing system of linear inequalities, that'll go super fast. You guys remember that. Solve a system of inequalities graphically. Now notice we took out the linear. And that's because you can graph any of the shapes that you have graphed coming up to pre-calculus as an inequality. So we're going to look at graphing inequalities with parabolas and with circles, along with graphing linear inequalities. And then the big piece de resistance right there. There's the end, the linear programming problem. Linear programming may not be that difficult. It's just that there's a lot of steps to get all the information that you need. So that might take us a little while. That's why I said we'll probably get one of those done today, but we'll save the 2 monsters for Monday. So reminder, an ordered pair AB is a solution of an inequality in X and Y if it works in all of the inequalities in the system. So in X and Y, if the substitution of X equals A and Y equals B satisfies the inequality. And that just means it makes it true. You plug in your solution, and it doesn't just work for one of the inequalities, because a system means we have more than one inequality. It works for every single one of them. It makes them true. Then it is a system. So the first thing we do, and yeah, I know this is kind of baby steps and below you a little bit here, but the first thing we do is we say, is the ordered pair 2, 5 a solution to the inequality? Well, all we have to do is plug it in and make sure the statement's true. So the y would be a 5, less than 2 times 2 plus 3. You do a little math in your noggin and say, hey, that's 7. And you ask yourself, is 5 less than 7? It's true. Now, that's not a system, because a system is more than one inequality. But that's how we test it. You know? If we want to know which way to shade that something is not solved for y, we can always test a point. If possible, we want to test the point 0, 0, because it's so easy to put 0. So a graph of an inequality represents all of the solutions of the inequalities, and that again is called a half plane. It's like a half a sheet of paper that just goes on forever. You know, something that's a plane would cover the whole planet, but a half plane would slicing that in half. Well, from there we have, remember that the boundary lines are important in that graphic representation. So with an inequality, we can't tell people all of the solutions. It's infinite. There are an infinite number of solutions. So what we have to do is show graphically, hey, it's everything I shaded here. And sometimes the numbers that are on the line are included. But this one is not that case. And that's because if this line is dashed, that means we're not including those. It is just a boundary line. It's a cutoff. So somebody that looks at it will know, hey, everything on that side is good. Don't use these. This is dashed. If they are going to use them, then we'll go ahead and make it a solid line, because solid means it's a part of our graph and it's a part of our answer. So this one says you'd graph y equals 2x plus 3 as the dashed line, and then y is less than 2x plus 3 would be the shaded area. But that line is dashed to indicate that there are no answers on that line. That is just a boundary. That's all it's there for. So down here, steps for drawing the graph of an inequality in 2 variables. We do a little pretending. We pretend it doesn't say less than, greater than, less than or equal to, greater than or equal to. So we pretend it says equals, and we graph the line. But then we stop pretending because we want to see, is it a dashed line? Was it just less than or greater than? Or is it a solid line because it was less than or equal to, greater than or equal to? So that extra equals bar is what gives us the ability to go ahead and make a solid line. And then, always a good idea, check a point in each of the 2 regions. So one on each side of the line, and see which one of them is true. And the side that is true is the side that you shade on. Speaking of shading, if you don't have colored pencils or at least 2 different colors today, you want to get in that bag and grab one. There should be colored pencils in everybody's bag. If not, let me know. And that's because, especially when we get to talking about the feasible regions, we need to know, okay, which of these equations hit which of these other equations. And if we do everything in pencil, we're not going to be able to tell that easily. It'll take us a little longer to figure that out. So this one, we're just graphing one inequality. This is not a system yet, but when we get there, then we're going to want multiple colors. All right, draw the graph of y is greater than or equal to 2x plus 3 and state the boundary of the region. So I start by pretending. I pretend it says equals. Then I need the boundary line. So this is hosting a T with your teddy bear. So we'll pretend. And then we look at that and say, well, we know how to graph that. That's y equals mx plus b. So if it's y equals mx plus b, we'd start at 3 on the y-axis, because remember, b is always the y-intercept. And then how do we use the 2? It is the slope. And you always use it as a fraction, so up 2 and over 1. And you can do that a couple of times so that you have something to aim at. Because without rulers, hard to draw perfectly straight lines. And then we pause. This is the important pause step, because we need to know whether or not that should be solid or it should be dashed. This one solid or dashed? Solid. We do have an equals. And that pausing is usually something students will forget every once in a while. Stop now. Was this supposed to be solid or was it supposed to be dashed? And then like I said, let's test a point. And typically most books will say test 1 point. This book does a great job, because if I'm taking a test, I always check 1 point on each side. But if you're doing 0, 0, it's pretty hard to mess up. So if your line does not go through 0, 0, that is a great point to test. So we take this point and we put it right back in here, where it will say 0 is greater than or equal to 2 times 0 plus 3, which will say 0 is greater than or equal to 3. No, it's not. So that means all of our solutions are not on the side that 0, 0 is on. If they were, 0, 0 would have worked. So our shading, and I can't really do a good job of shading up here without changing a lot of settings. So our shading would go in this direction. And that's what tells people, hey, anything that's on this line is a go, and anything that's over here, up and to the left, will also be a solution. And notice, we don't box it in or anything, because we want people to know this goes on forever. Everything over there is going to work. Now, when we're talking about a system, we have to do more than one of these on the exact same axis, because we want to know where do they overlap. Because that's where both of the inequalities, or all three of the inequalities, will be working. And that's a solution. So this one says the boundary of the region is what? Well, that was our pretend. Our pretend was y equals 2x plus 3. So that's what we do, whether or not it's a line or a parabola or a circle. We do this pretending that, hey, it says equals, and we graph what we know we're supposed to graph. But we do that pause to say, ooh, dashed or solid, and then we test a point. So these are just to remind us, what if they don't have y equals x plus b? What do we do for these things? X is greater than or equal to 2. Thoughts? What kind of line? Vertical. There's our pretend. There's our boundary line right there. X equals 2. I suppose if I put it down here because there's a nice space for it. Now, dashed or solid? Solid, we see an equals bar. And then this is pretty easy to shade. You don't really have to test a point. It says x has to be greater than or equal to 2. Well, that would be 3, 4, 5, 6. That's all this stuff out here. We shade that way. So, no big deal. In fact, it's a little easier if we don't have y equals mx plus b. So how about b? What does that look like? Horizontal line, y equals -3. Oh, dashed or solid before I get too far. Do not have an equals bar. Shade up or down? Down, less than. -4, -5, -6, all those down there. Is this all coming back to you? Full read. So whether or not it's the y equals mx plus b, or we're talking about horizontal or vertical lines, it's all been reviewed. Now, last year in Algebra 2, I don't think we got to graphing inequalities of parabolas. Nope, I know we didn't. We had to cut it off because there was something we had to put on the FCA. So y is greater than or equal to x squared minus 3. Here's our boundary. Oh, I'm going to put it up here anyway, so you can see it. Y equals x squared minus 3. What do quadratics look like when you graph them? Yeah, the parabolas. They're parabolas. Now, does anybody know exactly where this parabola is? Good. Starts at 0, -3. Exactly. And that's thinking back to our whole y equals a times x minus h squared plus k. This is x squared, but subtracting 3. So it's going to go down here. So now what I do is I use the fact that memorized y equals x squared. I mean, that was a parent function for the sake. You definitely want to memorize that and think, well, it was 0, 0, it was 1, 1, but then it was 2, 4, and it was 3, 9. And typically for a little negative 10 to 10, that's going to be enough. But that's with a vertex at 0, 0. So this is like my new vertex right here. I'm going to treat that like it's the origin. So to get some points from here, I'm just going to move 1 over and 1 up because I had 1, 1. And from this new vertex, I need to go over 2 and up 4. And from this new vertex, I should go over 3 and up 9. Now, why didn't I do a left side? Okay, just use symmetry. I mean, once you have this, you can use symmetry. You know that the vertex is at 0, negative 3, so just reflect over the y-axis. And you have it. So again, the parent functions really should be something we have memorized. We should know the feel of those. If you have to make a table, big deal. Make a table. Put 4 points in, you'll be fine. You get it. But now this is not just a parabola. So we have to ask ourselves if that should be dashed or solid. Solid, it has an equals. My best to round out my parabola. We absolutely do not want it to look like a V. Because what do you graph that gives you V's? Absolute value. Yeah, that might be in here too. You know what? I don't remember any absolute values. Didn't have any of those in there. But we're not done. I mean, normally we would have been done, but we have to shade. We have to know where to go. Can I test 0, 0 on this one? Yeah, my parabola is not on 0, 0, so I'm going to test 0, 0 in my original. And that will say 0 is greater than or equal to 0 squared minus 3. 0 is greater than or equal to negative 3. Is 0 bigger than negative 3? It is. Just to the right of it on the number line. So that means it works, and that means we shade in here. There it is. So whether or not it's lines, parabolas, circles, absolute value, steps are the same. Parent function's different, but the steps are the same. So I suppose I better fill in this little blank with the boundary here so that people are looking at just the notes. What we were doing. So far, so good? Okay. So let's keep going. A solution of a system of inequalities in x and y is an ordered pair x, y. Again, a system is not just one graph, at least 2. Might be 3, 4, multiple graphs. But it has to satisfy each inequality. It has to satisfy all the inequalities to be a solution. So that means we have a shaded region for the first one, and we have a shaded region for the second one. They got to be right on top of each other. We have to see that double shading. If there are 4 of them, we have to see quadruple shading to know that that's where the solutions to those systems are. It has to work for every one of them. So this one says, let's solve this system graphically. Okay, let's see here. So boundary for the top one would be y equals x squared. Well, we just used that to do the last one. Remember our little parent? 0, 0, 1, 1, 2, 4, 3, 9. Yeah, that's the one we need to graph. There's no HK on this one. Dashed or solid. This one's dashed. Don't get an equals bar. Dashed or dotted, whatever you need to do. We're not done with that one. We need Should I use 0, 0 as a test for this one? No, it's on my parabola. So maybe 0, 5. That sounds like a nice small thing to test. All right, so that would make this say 5 is greater than 0 squared. 5 is greater than 0. True? Last time we all checked. World's changing every day, but I think 5 is still greater than 0. Bottom one. What's that going to look like when we graph it? A line. Now this one's in standard form. And I know some of you really love y equals mx plus b. You could certainly do that. Solve for y. But remember, any added step that you take is a chance that you might do something wrong. So this is called standard form of an equation. And the easiest way to graph standard form is by finding the zeros. And we do that by a little something I called the thumb method when I used to teach Algebra 1, and that's this. We have 0 in position of the x. That means anything times x is going to be 0. So I can just cover that up with my thumb. And I can figure out 3 times something. Oh, I wrote 0 up against it. Ah. That means 3 times something will give us 4. And then can everybody just do that division in their head and see 4/3? No? Some people yes, some people no. All right. So then you'd actually divide by 3 on both sides. And get y equals 4/3. Then, with this 0, what we do is say, well, this is a y 0. I'm going to cover up the y with my thumb, and that says 2 times something is 4. Well, I know that's something. That's 2. And we have the x and y intercept for the graph. 2 points determine a line. Way back in geometry, point line plane postulate says 2 points determine a line. 0, 1 1/3, and 2, 0. Now, if you don't like that those points are really super close together, and you're thinking without a ruler I'm going to make a mess of this, you can always solve it for y and use the slope and get a better aim. Or if you don't remember the thumb method, you don't remember finding the intercepts, solve for y, graph it. So now dashed or solid for that one? Dashed. Hopefully I can try and get this kind of straight. Well, now I have to shade so we can see where the both of them sit. So can we test 0, 0 for that line? We can. Our line does not go through there. So let's test 0, 0. This would say 2 times 0 is 0, plus 3 times 0 is 0, and 0 is less than 4. Agreed? It is. So we need to shade down this way, which I really should do, so I'm showing my work. But remember, here's what we're interested in. Red and blue overlapping. Do you see it? Because now what we want to do is really over-exaggerate the shading in that region. And just really darken that in. That's what tells me, as a person that grades your paper, that you knew exactly where the overlap was for these two. And if you're saying, well, how are you going to be able to tell Cedar Home that we wanted dashed lines? I'll look at the portions of the graph that we didn't use to check and see if did you have it dashed, did you have it solid, what went through there. So that's just pretty. Let me put the colors in there. Are the points on the boundaries solutions in this system? Nope. They were dashed. Gotta be solid. They are not. Now, this says, use your graphing calculator to support your answer. Yeah, it's been a long time. You guys maybe don't know that you can graph inequalities on most graphing calculators. On the newer calculators, it's included as an app. Unfortunately, if you have a TI-83 Plus, ain't going to happen. The memory isn't big enough for it. But if we go under apps, and I've got a lot of apps on mine. Keep scrolling down until you get to I. In equals. That's graphing inequalities. So, couple of things with it. First of all, it takes a lot longer to do it on the calculator than it does by hand. Ashley, it's not doing whatever? You don't have it? Okay. When you take the ACTs or the MCAs and your memory gets cleared, sometimes, unfortunately, those apps will be deleted with it. You can always go grab your desktop computer and go to texasinstruments.com and you can re-download those apps. Or if somebody in class has the app, then we can use, I've got links. We can link them together and we can move them over into other people's calculators. But those of you that have the brand new color ones, it's there, it's hidden. So for the brand new color ones, you have to go to y equals, and then you have to arrow all the way to the left. And that's when it gives you choices of what you want to graph. So go all the way to the left and hit enter, and this little box is going to pop up and ask you, do you want equals, do you want inequalities, what do you want? So that's where that's going to happen. Find it?
Yeah, I was just saying mine has it like number 6.
Oh, was it in a different spot for anybody else? Anywhere in that list it can be. It depends on how they loaded it up. So in equals, okay, so some of you just did get that. Now the goofy thing about this is if you want to change this, what you have to do is use the alpha key. So you have to hit the alpha key and then any of these little graphing keys that are right below our graphing screen. So if I want less than, I have to hit alpha and window to get that to happen. And then you just type it in like normal. But again, it has to be self or Y, so extra little thing you do. Those of you that have it, you see how everything comes together? Okay. Because what it's going to do is it's going to do everything for us. It's going to do dashed versus solid, and it is going to do all the shading and all that good stuff. So it's definitely, for basic graphs, something you could do to double check before you hand in your test. All right. Now, to me, that thing is just annoying. So I usually turn it off right away. So I go back into my inequalities apps and turn it off. But if you're going to try it later and want to leave it on, do that. So now it'll just be equals for my calculator again. So we can double check. Solving a system of inequalities. Well, we definitely have more than one going on here. So the question becomes, what do I do with that? I mean, can I make my negative 10 to the 10 that I normally do? And given that there's a 14 in here, I kind of want to test that theory out. So what we do is we color code. I'm going to have this one be my red graph. And we found that find that boundary that we need. So with this one, I would again just really quickly do my thumb method and figure out what my zeros are. So if this is 0, something has to be 10, that something is 10. And if the y is 0, we cover that up. 2 times something is 10, that something is 5. Now I'm not going to graph that yet. Here's why. I don't know if the other graphs are going to have similar numbers. So I'm not going to rely on negative 10 to 10, especially with word problems. It's going to get really gross. So I want an idea of what my numbers need to be before I go over here. So I change colors, and I color code the next one. Notice how I put the color right next to it, so there's no question which equation it was. And I do the boundary, which is the equals. And again, find the zeros. So if x is 0, move my thumb up here because anything with x in it is going to be 0. Divide by 3, 14 thirds. I don't even worry about where that is right now. I just want to figure out what it is. And then if the y is 0, well, anything with a y attached to it is going to be 0. So 2 times something is 14, and that's 7. And then I stop and think. 14 thirds. Let's see, 3 will go in there, 4 and some change. Oh, I could have got away with a negative 10 to 10 window. But there's no negatives here. How do I know there's no negatives for this graph? These last 2 right here. X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. So why put all those negatives on there if we don't need them? We will just go ahead and go with quadrant 1. And let's see, our biggest X is 10. So we can probably just go by ones. In fact, if you want to spread it out, give yourself 2 units. And then for our Y's, we've got our 0, 10 and our 0, 14 thirds, and 10 will take care of that as well. Now we go back to the graph and see what's going to happen. So I'm back to my red, because that was the first color I used. I want to know where these things hit each other. And I graph 0, 10 and 5, 0. And then if this is for what we're going to do on Monday, which is going to be using our system of constraints, we would grab a ruler. We really want to know what it is. But this one isn't one of those. So we'll just go ahead and draw a line. Dashed or solid. Solid. And then we need to shade. So 0, 0 is an excellent one to try for this. So we'll put 0 plus 0 is less than or equal to 10. Sure it is. What on that? Well, and I changed colors because my second one was the blue one. Whatever you had for color, which one you use. And I figure out, well, 3 goes into 14 4 times, then we'll have a remainder of 2. So 4 2/3. And then 7, 0. Dashed or dotted. Dashed or dotted. Dashed or solid. Solid. Can we test 0, 0 for that one? Yeah, doesn't go through 0, 0. Our blue line doesn't hit 0, 0. So we test 0, 0. It's going to say 0 plus 0 is less than or equal to 14. Is it? Fabulous. So we shade down. Now, the last two, I normally don't do the shading for because it's kind of silly. I already made this graph so that x was greater than or equal to 0 and y was greater than or equal to 0. But I have to see that you guys know where x is greater than or equal to 0 and y is greater than or equal to 0. So you might just do a little something like that to show me, hey, this is the quadrant that I need right here. And then you got to go after that double shading. Got to go after it, find where it was. So on mine, that's going to be where is it red and blue. That weird looking little quadrilateral right there. Show that's got 4 sides. 1, 2, 3, 4. Right there. In this graph, are the points on our boundary lines, are they solutions of the system? They absolutely are. We had solids. Solid lines. There you go. So now, for this little bugger. Because guess what? We already did all the graphing for example 6. So this is example 6, just taking a step further. Linear program. That's Monday's big deal. We're going to start with just a teeny little bit of it today. Sometimes decision making in management science requires that we find a minimum or maximum of a linear function, which is called an objective function. You own a trucking company, or you're the accountant for a trucking company, and they're saying, we're spending way too much money on fuel. We need you to figure out a central location where we could move our business, where the fuel costs will be at a minimum. And that's really what a lot of trucking businesses will do. That's why sometimes you'll see them close down and position. Such a problem is a linear programming problem. We're given information that places limits on our resources. Usually it's money. Money is a pretty big deal. So this information provides what are called constraints. Things that hold you back. That's what constraints are. The solution of the system provides us with a feasible region. When something is feasible, that means it's doable. So our double shaded, triple shaded, quadruple shaded region will be called a feasible region. That means you could operate anywhere in that feasible region. But generally only one of them will give you the maximum benefits or the minimum costs. And all of those always occur at the vertices of the shape once you have the feasible region. So if our linear programming problem has a solution, it's going to happen at one of the vertices. And some books do call it corner points. I just feel like that's being awkward. And we know that in geometry, when you have a shape that has vertices, and those are the corners, that's where they come together. So you will notice this is exactly what we just graphed in example 5. 2x plus y is less than or equal to 10. 2x plus 3y is less than or equal to 15. X is greater than or equal to 0, and y is greater than or equal to 0. So I'm not going to have you regraph this. But here's what we need to do. We need to figure out where the vertices are on our fabulous drawing. And right off the bat, I'd say we can get at least 3 of them really easily. There's 0, 0. What was this one? The top blue one? 0, 14 thirds. We color coded. All we have to do is look at the colors. So there's another vertex that we have. This one over here, this was the red x-intercept. That was 5, 0. So there's 3 of them. This is the only one that's a maybe. If I had to guess, maybe 4, 1. You know we're not going to guess, right? We can find it perfectly, exactly. But 3 of these we know just from looking at the drawing. So let's go back and let's write down those vertices. All right, the nice ones were 0, 0, 0, 14 thirds. Oops. 141. And 5, 0, right? Okay. So we have one more we need to find. So I asked myself, since graphically, historically, is just not the best way to find intersections, could I figure out an intersection between, and I had this one red and this one blue without too much trouble? Well, yeah, algebra. That's what we could do. I don't know, we haven't done substitution in a little while. I think I want to do substitution. I'm going to solve for y in my red equation here. And then substitute that into the blue. That's going to get me my x value, and then I'll be able to substitute back in. So I will have, I better change colors here, 2x minus 6x plus 30 equals 14. Combine your x's. Subtract 30 and divide. 4. It wasn't 4. I was guessing when I said 4. And then I definitely was just a shot in the dark over the y. I thought maybe 4, 1, but it might be 4, 2 because it could have been a little higher. Well, all I have to do is put this back up in to that y equals equation, and I'll know what y is. So negative 2 times 4, that would be negative 8 plus 10. And that gives me a 2. There's my last vertex. Right there. So the other 3, we could see them. We knew what they were. But this one, kind of hidden. So now, let's see what they wanted us to do with this. It said, if this is a linear programming problem, find the maximum and minimum values of the objective function. Oh, there it is. the objective function. F equals 5x plus 8y. That's what you're trying to achieve. Subject to those constraints. Well, that means these four are the x's and y's that we're going to put into this equation. And we're going to see which one gives us the biggest number. That's the maximum. And we'll see which one gives us the smallest number, and that'll be the minimum. So for f equals 5x plus 8y, we had 0, 0. What do you suppose that'll give us if we put it in for x and y? Yeah. So unless we get a negative answer out of one, this is going to be our minimum. That would be the minimum production. Then we had 0 and 14/3, and yeah, if you don't like working with fractions, you can always pop that into the calculator. It's not going to be that bad. 5 times 0 is 0. All you're going to have to do is take 8 times the 14/3. And then, like I said, if you really don't like fractions, 1/12/3. But usually, we need to know about money and that type of thing. Your book does tend to use, I think there were like 5 problems, and 2 of them they used decimals, and the other 3 they used fractions. So whatever we need to do. So this gave us 1/12/3, but I might want to write down that that's 37.333. I'll have to check my answer in the back of the book, and that ends up being one of the answers. Then we have 5, 0. Plop a 5 in for x, we get 25. Well, that's not a max or a min. Already we can see that. That's somewhere in between. And then we had our nice little 4, 2. So we plop that in and see what we get. And that would be 20 plus 16. Aha! 36. So what we have to do now is write 2 sentences. And those sentences are about what we just found. So we would say the minimum of, well, it was 0. That was the smallest number we got when we plugged them in. Occurs at 0, 0. There's the minimum. And then we'd have to tell them about the maximum. The maximum of, what was our biggest number? 36. Occurs.
No.
Oh, thank you. Occurs at 0, 14/3. If you wanted to give that one as a decimal too, like I said, the book's kind of all over the place. Sometimes they do the fractions, and then sometimes they do the decimals. That is a linear programming problem. So that is a really good start, because this is the level that you did in Algebra 2. That was about as hard as your Algebra 2 stuff. But yeah, on Monday, and then we're going to be looking at much more, many more equations. So it says, here's one way to analyze a linear programming problem. By assigning positive values to 5x plus 8y, we obtain a family of parallel lines whose distance from the origin increases as f increases. The family of lines sweeps across the region of feasible solutions. Geometrically, we can see that there's a minimum and maximum value for f. I think we better hang on to that because you're catching up with stuff. So, you actually could do more than just the one assignment today. I know you'll want to dig into it, right? So, that is the assignment. If you know you're going to be super busy Monday night, because the linear programming problems, they take a while. We actually could do all but the last 3 problems on this one right now. 37, 38, and 40. And some of you maybe could do those just by extrapolating what we've been doing in class anyway. You know? But definitely make sure you finish up your 7-4 stuff. Because full credit on Monday, if you give me that. And at least do that 7-5 day one. Now we're caught up again. Next week. Finish up 7-5 with our linear programming, 2 days of review, test on Thursday. Unless, of course, you do know there's talk of a May 1st snowstorm. So, if something weird happens, we'll see. But yeah, there's supposed to be actual accumulation on Monday.
Do we need a graph? Do we need graph?
Yes, absolutely for this one. Yep, all kinds of graph paper over there. Help yourselves. Yeah, 7-5. Almost
No.
everything they ask you to do, you're gonna have to